So you can move your character to the right or to the left, and the character is not going to turn to the right or to the left. Sometimes you want to go around without having to turn the character. Therefore, the value of velocity squared is equal to a squared plus b squared. Move rot is where the character is moving. Aim rot is where the character is aiming. You can see that the aim rotation and move rotation is 0. When we work with third-person shooters, strafing is one of the most important mechanics to understand. Strafing allows your character to keep aiming in the direction of the camera while moving in different directions. And in shooter, this is critical because you want to keep shooting no matter where you move. Today, we're going to break down how strafing actually works. We will start with a simple visual example using a stormtrooper figure so we can clearly see the difference between movement direction and aim direction. Then, we're going to translate that directly into code. We will read the movement rotation, the aiming rotation, and the offset between them at every moment in the game. Understanding movement offset yaw is key to handling clean and believable character animations in Unreal. This is the Game Creator Accelerator channel, and I am Tony Munoz. Like, subscribe, share, comment, and ring the bell so you don't miss this series, where we are building a full third-person shooter called Mad Gameverse, all from scratch. All code is free for you. And if you're interested in building a consistent path as a game developer, not just learning technical skills, that path requires the right methodology, clear strategies, and long-term support. Visit Woolen.com to learn more about the Game Creator Accelerator Lifetime Mentorship and set a one-on-one chat with me. The link is in the description. Now let's get started. First, let's explain what is strafing in video games. Strafing means moving sideways without having to turn the character to face the direction. So you can move your character to the right or to the left, and the character is not going to turn to the right or to the left. When we're talking about shooting video games, this is perfect because sometimes you want to go around without having to turn the character. You want to keep aiming ahead of you or in front of you, even though you're moving the character to the right or moving the character to the left. Now, it's important to understand that in the world of Unreal, when we are talking about the X, the Y, and the Z axis, imagine that when you load the game, the north means that the X will be pointing forward. The Y axis will be pointing to the right, and the Z axis will be upward. Yaw is the rotation around the Z axis. So all yaw values lives on that flat plane that we are presenting here. Now, let's say that this is the camera of our game, and it's on the back of the character. Facing plus X, just X, will mean that the yaw is 0. Facing plus Y, completely just Y, it will mean that the yaw is 90. Facing minus X, it will be minus 180. Or 180 depending from where you're coming from. And facing minus Y will be minus 90. This never changes. This is Unreal's absolute reference. So in Unreal, you can call the world north if that helps your intuition to be that is totally plus X or yaw equals to 0. Now, if I am aiming forward with my character and I am moving forward with my camera, it means that the aim yaw is 0 and that the movement yaw is 0. That means that the difference between these two is 0. In other words, movement offset yaw is 0. This is why forward run animations have no strafe blend. Now, let's keep the aiming forward with the camera, but now I'm going to move my character to the right. So he's moving to the right, though the camera is aiming forward. In this case, the aim yaw is 0 and the movement yaw is 90. The offset is movement minus aim. In this case, it will be plus 90. That positive value tells the animation system we are strafing right. Now imagine that we are doing something to the left. The aim yaw is 0, but the movement yaw is minus 90. So now the offset is minus 90. Negative means that we are strafing left. Movement offset yaw is not a direction by itself. Movement offset yaw is the angular difference between where the controller is aiming and where the character is moving. Both measure against Unreal's fixed world axis. Keep in mind that when we are moving the camera, we're using the control rotation. And we're playing with computers, we use the mouse to control this rotation. So if we rotate, let's say, 45 degrees to the right, watching the world from the top, our base aim rotation will be 45 degrees. But if we are moving in the direction that is aiming the camera and the character as well, and we're moving forward, the offset it continues to be 0. But let's say if having these coordinates in the world, we rotate the camera 45 degrees, but now we decided to move the character to the left, then the offset between these two will be minus 90 again. So when we are strafing, we need to know the difference between these two vectors, velocity and base aimed rotation. And this is key to define how we'll use the animation later. This is the project as we have it right now. At the end, what we'll add are some indicators to understand how this offset yaw works. To begin, let's go to the C++ classes. And today, we are going to work on the player anim instance. The reason is because at the end, this will help us control the animation that we are going to use in our third-person character. Let's open the header file and go to the bottom until we reach this private section. Let's add an extra line and create a U property. In fact, I'm going to create a float first because now we can use AI to make this process faster. And let's name this variable movement offset yaw and set the value to 0.0. I will copy the U property on the top and paste it here. And now let's add a comment. Offset yaw to rotate the character to the movement direction when strafing. A very clear comment. Save and open the implementation. In the method of update any properties, we're going to check if this object, this character, is moving. To do it, we will use a new variable, which is the b is moving, which will be equals to bel, which is a vector we defined previously, dot size squared 2D, and we're going to compare it to a kinda small number. This is a very small number that is suggested by Unreal as well. It's very useful for not comparing directly with 0, but with a number that is infinitely small. Well, not infinitely, but very small. And let's add the corresponding comment. Is the character moving? Has a speed greater than 0? Now, first, let's create a const f vector vel 2D that we can define it this way, considering that we are not going to consider our movement in Z. We only want the value in X and Y. By the way, I forgot to mention why we use bel size squared 2D. We use the size squared 2D because movement offset yaw only cares about horizontal motion. It ignores vertical velocity and avoids expensive square root calculations. To explain why it's an expensive square root calculation, let's say that this is the vector of velocity. Following the Pythagorean theorem, you know that we have two components, which are a and b. Therefore, the value of velocity squared is equal to a squared plus b squared. We might be able to calculate the root square of all this to get the exact velocity, but I don't need to do that. I just need to compare velocity or velocity square with 0. And if it's bigger than 0, it works for me. If I would add another square root to calculate the square root of this addition, then we'll be adding an extra mathematical operation to process. And in this case, if we want to make an efficient code, we want to avoid that if we don't need it. That is why in our code, we get the velocity size squared 2D. Now let's continue. Let's create a const of the type boolean b has move there. And this will be bel 2D, the one we created a moment ago, dot size square, and we're going to compare it instead of a kind of small number to, let's say, 25f. As the suggestion here, this will avoid problems when the speed is very low. Size square returns the square length of the vector. It is like the speed squared. We compare it to 25, which is 5 squared. So this means only treat the velocity as a real movement direction if the speed is greater than about 5 units per second. Why size square instead of size? It avoids a square root, so it is cheaper in terms of the calculation. Why it matters? Because when the character is almost stopped, the velocity direction becomes unstable and can flicker because tiny floating point values bounce around. This check avoids using a noisy direction. Now let's add an F rotator, aim, rotation, which is equal to shooter, character, get, control, rotation. Is the shooter character, I have to change this one here. Now it looks great. This gets the controller rotation, usually driven by the camera. In a shooter, the camera yaw is often the real aim direction the player expects. Why this matters? You're measuring the movement direction relative to where the player is aiming. Using control rotation makes strafing feel correct when you rotate the camera. Now let's set the aim rot pitch to 0 and the aim rot roll to 0. The first one removes up and down rotation from aim. Pitch is looking up and down. For strafing and locomotion offsets, pitch is not useful because the character moves on the ground plane. Roll is tilting the camera sideways. Usually roll is 0 anyway, but we force it to be safe. Setting these both variables keeps the rotation clean and stable. We're only considering the yaw. If you're following this video and this series, it is probably not just because of this game. It is because you are interested in building a solid and consistent path as a game developer. And I know how challenging that can be. That path takes more than technical skills. They matter, but they are not enough. It requires the right methodology, clear strategies, and a system that helps you stay focused on what actually matters. It also requires feedback, accountability, and a community of creators walking the same path, so you're not figuring everything out alone. How many times have you started only to lose direction and end up frustrated with not real progress? How much longer are you going to wait before committing to the path you actually need? If that resonates with you, visit woolen.com to learn more about the Game Creator Accelerator Lifetime Mentorship. See how creators from different backgrounds are building their path toward independence as a game developer, and set a one-on-one chat with me. It is woolen.com and the link is in the description. Now let's continue. Now we're going to the if to check if B has moved a direction. I'm going to remove these two lines for a moment and explain some details. The B has moved direction first. This will only compute a new movement direction if we have a valid movement direction. If the character is basically standing still, we do not recompute offset, which prevents jitter. This first line inside the if converts the 2D velocity vector into a rotation that points in the direction of travel. As an example, if the player moves forward, move rot yaw points forward. If the player strafes right, move rot yaws point right. This becomes your movement direction reference. Now let's make the move rot pitch equals to 0 and move rot roll equals to 0. You see that we declare it as a constant, then we can change it. So what I will do is remove this const. The move rot pitch equals to 0 forces the movement rotation pitch to 0. Even though vel2d has set equals to 0, this keeps it explicit. Again, we are considering yaw only. And the roll forces the roll to 0 for safety as well. Now let's open more space to set the movement offset yaw. This will be a U Kismet math library normalize delta rotator, passing move rot and aim rot, and getting the yaw. Because I'm using the Kismet math library, let's add it here in the include. And now go back to the button and no errors. This is a key line. It computes the difference between two rotations and normalizes it to a clean range, typically from minus 180 to 180. I'm talking about degrees, of course. Move rot is where the character is moving. Aim rot is where the character is aiming. This delta or offset tells you how far the movement direction is from the aim direction. Let me tell you some examples. If you aim forward and move forward, offset is about 0. If you aim forward and strafe right, offset is about plus 90. If you aim forward and strafe left, offset is about minus 90. If you aim forward and move backward, offset is about 180 or minus 180. This single value is perfect to drive a strafing blend space, a directional blend, or a turn-in-place logic, because it tells animation exactly where movement is relative to aim. And now is a great moment to present this information in the screen so we can understand what is happening. So after this last line, add F, G engine, and here are 3 great suggestions. One for the movement rotation, we can call it movement rotation. Another for the aim rotation, and a last one for the movement offset. I'm going to leave the movement offset for a second on one side and remove the comments for these two. You can move these to another line so you can read them. And what we are doing is just presenting on the screen a screen debug message. We're using the color green, and we're presenting this information which is related to the move rotation to string. And we are dereferencing these values. Let's save, confirm that you also saved the header, and go back to Unreal. In Unreal, let's compile. And now let's play it. Look here to the corner. As I'm moving my character, in fact, let me start from the beginning. If I move my character ahead, look, the aim rotation and the move rotation is 0, both of them. Now let's go and move backwards. Now you see that the move rotation is 180 on Y. In fact, I'm going to make some changes to make this clearer. From here, I'm just going to use the move rot, and take the component of yaw. And in the aim rot, I'm going to do something very similar. Just the component of yaw, because at the end, it's the only one that matters to me. Save, and go back to Unreal. Compile. And we have an error. Oh, the error compilation is because this is an S. Let's change this to an F. Compile. Compile in Unreal. And now we don't have errors. Let's play. And if I move my character forward, you can see that the aim rotation and move rotation is 0. Why? Because the aim rotation and the moving is going in the same direction. Let's move now backwards. Now we have that the aim rotation is 0, but the move rotation is 180. It makes sense because we need to move kind of backwards even though we're looking forward. Now let's move to the right. You can see that the aim rotation is 0, but the move rotation is 90. That's correct because we're moving to the right. And if we do it to the left, you can see that the aim rotation is 0 and the move rotation is minus 90. Everything makes sense. And if let's say I'm going to rotate something like 45 degrees and then move forward, you can see that it's not 45, now it's kind of 45. The aim rotation is 47 and the move rotation is 47. When things are starting moving is at the moment that we change the rotation of the camera, but then they eventually establish what will be the aim rotation and the move rotation. I recommend you to play with this until it makes sense for you. Now let's stop, go back to the code, and let's get the final element, which is the offset. Let's move this one to the next line, and I'm going to comment these two. I don't need them anymore. Save, and back in Unreal, compile. Now we'll check the offset. Look what happens. Let's move forward. Now you can see that the movement offset is 0.03, almost very close to 0. But if I move in any direction, eventually it also goes to 0. So this is happening because we are consistently adjusting the value of what we are watching, of what is in front of the camera, and what is the direction that we are taking. Again, take your time to understand how this works before going to the next step, which will be adjusting the animations corresponding to the movement and to where the camera is looking at. But understanding these principles is key to what is coming next. Now you understand how strafing works, how aim direction and movement direction relate to each other, and why movement offset yaw is such an important piece of your animation system in Unreal. In the next videos, we'll keep building on this and refining the movement and animation logic step by step using what we learned today. To support this channel, like, subscribe, comment, share, and ring the bell so you don't miss the next videos in this series, where we continue building and refining our third-person shooter. Don't forget to visit woolen.com to learn more about the Game Creator Accelerator Lifetime Mentorship and set a time to chat with me one-on-one. The link is in the description. And I want to invite you to watch my full free training where we'll start breaking down how to approach the gaming industry step by step. No hype, no shortcuts, just a clear process to build skills, visibility, and real opportunities over time. And until next time, keep creating, keep sharing, and most importantly, keep dreaming big. I'll see you soon, my fellow creators.